Good morning, DebConf. So this is me. I've been involved in Debian since about 2003, and I've been working on the Linux kernel and some of the code around that, both for Debian and in my paid work since about 2008, so over 10 years now. So I'm a member of the Debian kernel team. I'm also on the LTS team. Most of my work there also relates to keeping the kernel up to date. So I'm doing quite a lot of the kernel packaging, and I'm also often backporting fixes to stable and older releases that need them. At one time, I maintained some of the official long-term stable branches at kernel.org that were needed in Debian, but I'm free of that responsibility now. As you might know, Linux releases work fairly often. There are about 5 major feature releases every year. There's a 10 to 11 week, 9 to 10 week cadence there. And then for each of the supported stable branches, there's usually a stable update every week or so. So because of the quite short release cycle, sometimes features that go into, sometimes features are not quite complete in their first release, and they take a few further releases to be fleshed out. And besides that, quite a few kernel changes don't stand alone. They need changes in user space and other supporting packages to actually take advantage of them. They might need a new user space tool for configuration. There might be an existing user space tool that needs some additions. If there's a new API that's meant to be used by all kinds of applications, then we have to wait for those to actually take advantage of that. And sometimes there need to be packaging or other infrastructure changes in the distribution to enable the feature. In this year's talk, I'm mostly going to be talking about changes that have occurred since Linux 5.10, the release that went into Bullseye. Starting with a recap of features that I've talked about in previous iterations of this talk. The RISC-V open architecture is still fairly new in its Linux support. So it's been getting support for some of these features that you expect to see in other architectures. It now has support for virtualization using the KVM hypervisor facility. It has support for general performance monitoring events. The RISC-V architecture has a couple of performance counters for number of instructions and number of cycles. Those aren't terribly useful, but there's now an extension for performance monitoring units, and that's supported by the Linux perf events subsystem and the perf user space tool. It has more support for tracing, kprobes, uprobes, and ftrace. It has support for kexec, which allows you to boot into a different kernel without taking a trip through the bootloader. It has support for transparent huge pages, which improve the performance of processors using a lot of memory. And it has support for virtually mapped stacks, which mean that stack overflow normally reliably results in a crash rather than in arbitrary memory corruption. The IOU ring subsystem, which is the new way of doing asynchronous I/O on Linux, has added support for more operations. So I think pretty much any I/O you want to do can be submitted through IOU ring now. The worker threads that are used to implement that now run within the context of the process that scheduled the I/O. Whereas previously there was a shared pool of worker threads which needed to change context. So that improved performance a little bit. It also means there's less risk of bugs where I/O is executed in the wrong process, which would be a security disaster. That's also integrated with the audit subsystem and Linux security modules. So if you have restrictive policy on what processes can do what, I/O earing is no longer a way to escape that. And there are more user space programs taking advantage of that within Debian. I've got a list there: MariaDB, at least in the RocksDB backend. plocate, which is now the standard locate implementation. QEMU and Samba can take advantage of it, and I think most of those already did so in the Bullseye release. The extended Berkeley packet filter, which is really quite a misnomer now, so we'll just call it eBPF. That's an API that's being used to extend the kernel by adding user programs that control or monitor what's going on at different points in the kernel. In 5.10, we had the BTF, Berkeley BPF type format, which is a lightweight debugging information that allows BPF programs to introspect the kernel. That's now supported in modules, so your BPF programs can look at what's going on there. The programs can now carry out atomic operations. They can register for timer callbacks, so the program will be called with a specified delay. The mapping structures that they can use can now be used as Bloom filters, and compile once, run everywhere, which is supposed to allow you to build a BPF program and load it on a different kernel version or any kernel version where the APIs haven't diverged too much. That's now implemented in the kernel. It's not reliant on user space for that. That lays the foundation for signed BPF programs. But we certainly haven't implemented that in Debian yet. And there are many new helper functions for BPF programs, many new hooks where they can be installed. However, eBPF is now basically disabled by default for unprivileged users. Unfortunately, BPF is so powerful that it's been the cause of a lot of security issues where unprivileged users were able to modify data in the kernel and then potentially get code execution. So it's for disabled by default unless you have capsysadmin, which is essentially root equivalent, or the BPF capability. That change has also been applied in all the stable branches. So a couple of changes for sandboxing. The seccomp system call is used by many applications to limit the system calls that they're going to be allowed to execute in future. Applications can do this themselves, or this can be imposed by an external manager like Docker, which can confine containers, and systemd can use that to limit what a given service can do. And then there's Bubble Wrap, which is used by Firefox and Flatpak, I believe. So seccomp filters are written in classic BPF, so that's classic BPF is still available to unprivileged users. That is able to look at all system call arguments, although it's not able to chase pointers, so it can't look at the paths that are being passed into a system call. That makes it quite flexible, but slow. But it turns out that most of these filters are just looking at what was the system call number. All they're interested in is blocking or allowing specific system calls. So the kernel will now emulate a call through the filter with each of the possible system calls that it supports. If it discovers that the program would always allow that system call number without looking at the arguments, then it can use that to build up a bitmap of always allowed system calls, and in future it can bypass the program by consulting that bitmap. So the result of that is most sandboxed programs have got a little bit faster without any changes required in user space. So we all have another different sandboxing mechanism, which is the Landlock Linux security module. Unlike seccomp, that works in terms of I/O operations and paths. This is quite similar to the Capsicum API implemented in FreeBSD and the pledge and unveil system calls that OpenBSD has. Again, any process can use this to restrict itself. Currently, it only works with file system operations. I think originally it was intended to cover network I/O as well, and maybe that will be added back in later. So for containers, and well, not just containers, we have a new feature of IdMounts. User namespaces have been around in Linux since the late 2.6 versions, and those remap the user IDs and group IDs that are seen within a container. As an example, you can, as user 1000, you can create a new user namespace where you appear to be root, you have UID 0, but on the outside of that container, you'll actually still be seen as having UID 1000. File systems, at least up until now, have always stored the UIDs and GIDs seen in the root user namespace, so the global IDs. So if you want to run a container in its own user namespace, or if you want to run multiple containers in their own user namespaces, they each need to have different ranges of UIDs and GIDs. They would have a different idea of which global UID is root. And that would mean that they couldn't share a root file system, even read-only. Because the files that they would expect to see as being owned by root would need to be owned by each of their versions of root. So the solution to that that's been added in 5.12 is IdMounts. They add an extra mapping between the global UIDs and GIDs and those that are stored on disk. It needs support in each file system, and that's now there in most of the popular file systems that use block storage. It's also supported in OverlayFS. Systemd is already using this for so-called portable services and portable home directories that use a file system image that may need to be mapped to the user IDs and group IDs of the host that it's used on. Containerd, which is used in Docker, and I think Kubernetes, should use this, but doesn't yet. There's a merge request open upstream to do that. So Linux, as a preemptive multitasking operating system, allows a running task to be preempted whenever it's used its fair share of time, or if a higher priority task is woken up and needs to use the CPU. When a task is running in user space, it's always preemptible, but when it's running in when it's in a system call, it may or may not be. And for a long time, the build time configuration of Linux has given you the choice to allow preemption never during a system call, only at specific points, or all the time, excluding a few sections where it would be unsafe. And there's a trade-off there between throughput and latency. If you don't allow preemption in a system call, you can get higher throughput. If you allow preemption almost everywhere, then you get lower latency. For servers, often we want higher throughput. Desktops, we want lower latency, or that's historically been what was thought. Debian doesn't build two separate configurations, so we compromised on the middle option there. But since 5.12, there's the preempt dynamic option, which is enabled, and that allows you to choose at boot time which of those three preemption models you want. At least on x86, it's I think available on other architectures, but not enabled by default, as there's some performance cost. That choice does not include real-time preemption, which requires far more widespread changes in the kernel. So, given that we think servers possibly want the preempt none, and desktops might want the other options, maybe the installer should be setting this on the kernel command line now. I'm not sure. Something to think about. So core scheduling, a bit of background for this. System multi-threading, or what Intel calls hyper-threading, allows the operating system to schedule usually two, but sometimes more threads on the same physical core. Depending on the implementation, those might take turns, but in most implementations, the two threads are instructions from the two or more threads are running at the same time in parallel on the core. And that allows the core to make use, to keep more of its execution units busy, which it doesn't give you twice the performance, but it does give you a small boost in performance for most applications. The unfortunate result of this, though, is that because those threads are sharing resources on a very fine-grained basis, there's a side channel between them, a timing side channel with very high bandwidth. It's it's possible for one thread to know quite a lot about what the other thread it's showing the core with is doing. That's not a new problem. It's been something that researchers have warned about ever since SMT was implemented on the Pentium 4. But the recent speculative execution attacks have increased the severity of this. And that sharing of resources also means that the performance of the thread is not that predictable, which is very bad for real-time systems that want predictable behavior. So the kernel really shouldn't let threads that run in different security contexts share a core, and it shouldn't make a real-time thread share a core with any other thread. Currently, it does by default. But the core scheduling allows user space to say, to define which threads should or shouldn't share a core with each other. Containerd and LXC container managers now both provide the option to isolate containers in this way. It's not on, doesn't seem to be on by default, but it is there as an option. You would probably want this to enable this for isolating virtual machines as well. So far as I could see, QEMU and libvirt aren't doing this yet. So more on real-time. There have been several different things called real-time Linux, but what I'm talking about is the preemptrt patch set. That adds the ability for the Linux scheduler itself to do real-time scheduling. And that's really important for industrial and safety-critical applications where if things don't happen on time, people might die. It's also useful for media production where the stakes are a little lower, but no one wants to see stuttering video or audio. That's been developed since, I think, around 2005. The developers are also active upstream, but until recently, only small parts of those changes actually went into the upstream kernel. I had a look back at 5.10, and there, the patch set for 5.10 changed about 16,000 lines. For 5.18, it's less than 4,000. In between those versions, most of the big changes actually went upstream. And what's left is mostly fixes for drivers that do things that don't work right in a real-time configuration. And there are a couple of new traces specific for real-time Linux. There's OS noise, which is supposed to measure how long the kernel interrupts a user space program for, and timerlat, which measures the latency between a timer going off and the code that's been scheduled to run actually running. There's a front-end tool for those called RTLA that's included in the kernel source, and I will be adding a new binary package for that. That's committed to Git. So the next upload of 5.19 should have that package. There's a new option for Windows SMB file sharing. The standard implementation for that has been Samba in user space. KSMBD is in the kernel, and that should mean higher performance in general. There are also a few features that have been added there that aren't in Samba yet, but that doesn't seem to have integration with Active Directory, so if that's something you need, Samba, you'll have to stick with Samba, I think. That's managed with KSMBD tools, and there's already a package of that in Debian. An image that should strike fear into every setadmin's heart. So we have a file system health reporting API that's been added into the FA notify system call. So there's the option there to enable reporting of file system errors that are not specific to a process. There are things like data corruption or an IO error. In order for that to work, the individual file system has to support it, and so far only ext4 does. Hopefully we'll see that extended to other file systems in future. I couldn't find any user space in Debian that's actually using that. It seems to me that udisks or systemd should be listening to this, but maybe it's something that should be done at a higher level with Prometheus, Munin, whatever. And now a kernel internal change, memory folios. The kernel memory manager generally deals with pages of memory as defined by the hardware memory management units. Those are the units used for virtual memory, and depending on the architecture and the configuration, they can be between about 4 and 64 kilobytes. 4 kilobytes is a pretty small chunk of memory these days. Pages can be allocated in groups and managed as compound pages. However, inside the kernel, those will still be referenced as pointer to struct page. There's no differentiation in type until recently, anyway. The result of that was the kernel had a lot of checks to see whether a page was the start of a compound page or what we call a tail page, something that appears later inside a compound page. And there were a lot of bugs where it assumed wrongly. The Folio API distinguishes compound pages from single pages, and that has enabled removing a lot of checks. It should avoid that sort of bug in future. And actually, some areas of the kernel are now being changed to support compound pages properly, which should bring some performance improvements. Right. So this is kind of a bug fix, but kind of a rewrite, in fact. When programmers write to a block device, or usually they write through a file system to a block device, unless they're using direct I/O, those writes are going to be buffered in memory, because waiting for the write to go all the way to the device is slow. So those writes, of course, are going to have to be written back eventually. If storage is quite slow and programs are writing to memory faster than that memory can be written back to the device, then we have a problem. And if that doesn't stop, memory is going to be full of write buffers. So the kernel will try to detect this kind of congestion, and it will block tasks that are writing for a while. The intent was that they would be blocked until the congestion cleared or up to a timeout. Not all of the block drivers actually signaled that congestion was cleared, and there was a big rewrite of the block layer a few years ago that broke this entirely. So the result was that tasks were being made to wait longer than they really should, which also is bad for performance. And that has been fixed in Linux 5.16, but because it's a complete new implementation, that won't be backported. So that's something to look forward to if and when you upgrade some improvement in IA performance. The Linux random number generator has been around for ages. And it's seen quite a few changes in recent versions. There's no real change to the architecture, but it's now using more conventional cryptographic algorithms to combine the various sources of entropy into a pool, and then to extract a stream of bits from that pool. The Intel CPU random number generator instructions recently got a bit slower because it turned out you could snoop on old random numbers from there, and that was really bad. So there was a microcode fix that made those a lot slower. The Linux random number generator relies less on those instructions now, which should improve performance. The bootloader or UEFI firmware can provide a random number generator, which is useful when the kernel is just getting started. If that's available, then that will be fed into the entropy pool by default. The CPU random number generator instructions will also be used as an entropy source by default now. Some people don't entirely trust those, but you can always turn that off. And those are mixed in a way that means even if they're predictable, it doesn't totally compromise the random number generator. All of those changes have unusually been backported to the stable branches that's still maintained. There's also a jitter-based entropy generator where if the kernel hasn't found enough entropy at boot time, it will do some scheduling that should have somewhat unpredictable timing, and as long as you have a high precision timer in the system, that should provide entropy for the random number generator at boot time. So on most platforms, that means even the dev urandom device, which used to be considered maybe not that great, is going to provide secure random bits right from the start. And on ARM64, hardware random number generators available through firmware calls or special registers are also being fed into the kernel random number generator now. We have a few more changes for mitigating security flaws in the kernel, or hardening. On some architectures, the kernel stack pointer, or the initial stack pointer at the beginning of a system call is being randomized. There are some exploits that rely on setting up data on the stack with one system call and then carrying out a second system call that doesn't initialize its buffers and then reuses the data from the previous call in a different way. By randomizing the stack pointer at the beginning of the system call slightly, it's no longer possible to have that kind of alignment reliably. So this is being built on, but because it has a slight performance cost, it's not enabled by default. You have to set a kernel parameter if you want that. The mem copy move and set function calls in the kernel we have so-called fortify bounce checking on those. But until recently, they allowed writing up to the end of a structure. If you had an array embedded in a structure, they could actually overrun the array to the end of the structure, and that was allowed because, unfortunately, there were a few places in the kernel where that was done legitimately. That's now been cleaned up, so they will bounce check to the end of the array. VMAP stack, which protects against stack overflows, is implemented on a few more architectures. I already mentioned RISC-V, but it's also there on ARM 32-bit. And that adds to AMD 64, ARM 64, and S390X, which already had it long ago. We're also seeing the beginning of control flow integrity. So on most popular architectures, you can't simply inject code into the kernel if you overrun a stack or heap buffer. All the memory that's writable is not executable. All the memory that is executable is not writable. And you can't, if you can fool the kernel into jumping to user space, that doesn't work either because user space memory isn't executable in kernel context. So attackers have to take advantage of return-oriented programming or jump-oriented programming, which involve overwriting either return pointers on the call stack or indirect function pointers in operations tables. The idea of control flow integrity is to catch and block that kind of attack. For the return stack, it would add a shadow stack that's entirely separate from local variable storage and couldn't be overridden by stack buffer overflows. For jump-oriented programming, the protection would be it's complicated. So there is a software implementation of this for ARM64, but it depends on features in the Clang compiler. And we're still building the kernel with GCC on all architectures. So we haven't enabled that in Debian. There's a very limited implementation of x86 that relies on Intel CET that's available on some of their recent CPUs. That's not enabled yet either. I'm not sure that it's worth the trouble given how little it actually protects. And finally, some changes to the package. We've added configuration options to enable some new SoCs and platforms. ARM64, we have support for Hyper-V. I'm not sure if that's actually a retail product, but the Azure cloud has support for ARM64 now, I believe. Also the Qualcomm Snapdragon 845 SoC. We've got support for the Marvell MMP2 and 3. We've got support for a couple of new RISC-V SoCs and some x86 chips. The configurations for different MIPS platforms are now a bit more consistent, and for all MIPS architectures, we now have a generic flavor, which I think should support newer platforms, if there are any new platforms. Unfortunately, the older platforms still need their own flavors. The perf utility in the early days tended to depend on new kernel features, so we tried to run a version that matched your currently running kernel. That doesn't seem to be needed anymore, so we've simplified things there. Linux perf is a regular package, not a meta package. And so you can run the latest version of that against whatever kernel you're running. And we've implemented continuous integration on Salsa. That required adding a quick build profile that is meant to cover most of the code, but will run in a not too terrible length of time, despite the CI runners on Salsa being a bit slow. Another benefit of that is if you have a fast build machine, you can now do that build in about 10 minutes. And in the process of that, I also fixed warnings from the build log hardening check and all the linting errors. There are still a few warnings left, though. Right, so we have about 5 minutes for questions.
Anybody for questions?
Come on, there must be something.
My question is the SDE845 stuff for the Qualcomm devices. Do you know if it already boots one of the Qualcomm-based phones? Did you get any feedback on that, like the OnePlus 6?
I don't know about that.
Okay.
I wouldn't think so, but I'm not really involved in the ARM hardware support.
Of course, I don't understand everything what you say, but you mentioned a part about I/O to disk, which got faster, and I think for the infrastructure that we run for CI.Debian.net, disk I/O is actually, I think, the biggest bottleneck. Do you think that could help there? I think you mentioned the kernel is that it's not unstable yet, I think.
Which was this you were talking about? The where? It was there somewhere. Do you mean the right throttling or something different?
Yeah, I think so. Yeah.
Yeah, I don't know exactly how you would tell whether this was whether this is affecting you.
I'm not totally aware of which version of Linux isn't stable, but
Stable has 5.10.
okay. Do you think it would be worth trying, or should I first try and figure out?
Sure, yeah.
Anyone else?
Hello, Ben. I only want to thank you because your great work always with the Linux packaging in Debian, and keep going the great work.
Well, it's very much a team effort, so don't just thank me.
So, hi Ben. So yes, the system call filtering we found on a work product makes a huge issue. If we tried to lock down every single one of our system services to just the system calls it wanted, and on a system call heavy process, it was really noticeable. It massively slowed down throughput. So yes, we've been following this, and it's nice to see that it's going in the kernel. There are changes around eBPF and also the userland half of it, which name I can't remember.
That's libbpf.
Yes. I think libsetcomp as well also needs
Right.
updates. And it should make life much, much better. We've been watching this. We'll be sure to give feedback if we find that there's anything more needed in Debian.
Thank you.
We've got about another 2 minutes for questions, so anybody? Looks like we're set then. Many thanks to Ben. Go and enjoy lunch.